Hello, and today we're going to continue our exploring of our understanding of geological maps through looking at unconformities and igneous intrusions and how those look on the map. So, as you may remember from last week, essentially we've been learning how to use structure contours, which allow us a quantitative description of 3D surfaces, right? So we can use 2D maps to understand how geological structures behave in 3 dimensions. And we also learned how to use structure contours to calculate the dip and the strike. The spacing and the scale of the structure contours help us to define and understand that. And also we saw how the interaction between the topography and the structure contours allows us to predict where the outcrop is going to occur. And hopefully you also learned a little bit about intuitively interpreting geological maps using the V rule to try and understand which way stratigraphy might be dipping by just looking at the map pattern and comparing it with the topography. So today what we're going to do is try and understand a number of different new concepts, particularly starting with inliers and outliers. You'll see what that is in a minute. We need to better understand the 4 different styles of contacts that we find on geological maps, and also how to deal with maps that have more than one set of structure contours when all the contours are not parallel to one another, as we experienced last week. And going along with that is the understanding of unconformities, which also have their own structure contours, and again igneous intrusions, which don't behave in the same sort of way, although when they're planar we can also draw structure contours for them in that situation. So firstly, let's deal with inliers and outliers. What on earth is an inlier and an outlier? Well, these are essentially things that we see on geological maps, and they reflect the impact of topography on the outcrop pattern. So in the case of an inlier, this is where we have 2 rock units, one older, one younger, and by virtue of a depression in the topography, you're able to see through essentially a hole in the top unit to see the exposure of the lower one, and this will look like some sort of a blob on the map with the older unit surrounded by the younger one, like that. And you can probably already guess an outlier is exactly the opposite. This is where we get higher, younger rocks exposed on a high point. Purely, they're just preserved here because of the erosion, and so again on the map what you're going to see is a blob, in this case of this purple stuff surrounded by the blue, and we call this an outlier. Typically there is a wider band of the purple material, the younger stuff, further away. So there are just erosional reasons for this, but also sometimes these are related to the presence of flat-lying faults. So for example, in this particular case, if the base of the hill here, which forms the outlier, we call this a clipper, and conversely we call it a window when you're looking, if the top unit here is thrusted into location by faulting, then this window, this inlier, is actually, then we call that a window when it's generated for tectonic reasons. So now we're going to quickly look at different types of geological contact. So, because the most standard and the one that you dealt with last week are conformable contacts. So this is essentially where a bunch of usually sedimentary rocks are piled up one on top of the other, and essentially there's no break in between them, nothing that we can see or notice anyway. So this is, as the thing says, this means it's within a succession. So when you might be simplifying a geological map, these are the sort of things that you might eliminate. because they are separating parallel bedded units. So for example, here we have a red unit and a white unit with a contact between the two, and there's no break really. There's a change in colour, but there's no erosion or folding or anything like that. And that means when you're in a continuous sequence like this, it means the conformable contacts don't touch each other. Right, they're like you were doing last week, they're usually parallel to one another. And of course, if you can have conformable contacts, it means you can also have unconformable contacts. And in this case, this is where we have one older set of rocks, which are, in this case, you can see they're steeply dipping here. This well-bedded, looks like sandy sort of rocks here. And what we have on top of it, there is an angular discordance here between the steep dipping rocks underneath and the flat bedded stuff, this red material on top here. And what this represents is an erosion surface. So a number of things have come to pass in order to make this happen, that essentially these sediments were laid down and then they were folded and uplifted, eroded, and this younger unit has then been deposited on the top of it. And so this is what we call an unconformable contact, an unconformity, and you can spot them because the dip on the below and above are different from one another. And you often see them on maps because it makes a sort of a T shape on the map where this older stuff is juxtaposing against the younger material. So there are different styles of unconformity. Like the one you just saw, there are angular unconformities where there's a sequence which has been tilted and then eroded. There are disconformities where the sequence is uplifted and eroded but not, it isn't folded, so they're still flat lying, and the bed boundaries in the upper and the lower sequence might even be parallel to one another, but you have had an erosion surface that we call a disconformity. And finally there's the non-conformity, and this is where we have igneous rocks, massive igneous rocks that don't have any bedding in them underneath, and they have been eroded and covered over by sediments. So all of these look fairly similar on the geological map, but the T that we were really looking out for is particularly unique to the angular unconformity. Another type of geological contact that we see on the maps are intrusive contacts, right? So this is where we have liquid magma has been injected into place within a pre-existing rock. There could be an igneous rock, it could be a bedded sedimentary rock. So you can see in this picture here we have at least two generations of intrusion going on here. We've got the grey rock in the background, that was the original material, and it was broken, and this white looking stuff has been intruded in there in the first stage, and secondly it's been cross-cut by the black thing here, which is called a dike. So the cross-cutting relationships here tell us about the relative age of the different units. The grey is the oldest and the black is the youngest. And you can imagine what that would look like on a geological map. This black thing is cutting right across, and if it's very vertical, which they often are, it can just cut straight across the map, and it's rather clear to be able to see those when you examine. So let's have a look at this. So different types of igneous intrusions. So here you can see a sill. A sill is a flat-lying intrusion that is injected within a sedimentary sequence and is parallel to that. So it's a tabular igneous body of frozen magma, and however it doesn't cut across the sedimentary units, and it's got this sheet-like form. So, however, if it does cut across the stratigraphy, across the sediments, the bedding like this, we call this a dike. Sometimes they're vertical or close to vertical, like this example, but they don't have to be. The critical thing here is that they have to cross-cut, and they also have a sheet-like morphology, right? So both the sills and the dikes are tabular. One is relatively flat, the other one is more high angle. And the critical thing is that cross-cutting relationship here. So the third style of igneous intrusion we have are called plutons, and those are essentially big blobby masses which are intruded into the bedded sequence. They also, like the dike, they are cross-cutting the stratigraphy like this, and typically you might notice these because, well, first they're not tabular, and secondly they have this weird irregular margin that you can see here. So the other type of contact you might see on a geological map is a fault. This is a brittle sort of contact. A fault is, maybe as the name suggests, a place where the rock sequences, in this case these bedded sedimentary rocks, have been broken in a brittle fashion, and there has been some displacement across that. You can see, for example, this black unit here that this guy has got his hand on has been offset. It's dropped down here. This is an extensional sort of fault, but the direction of motion on the fault doesn't have to be extensional. The different styles of fault, as you'll see when we do the exercises, and essentially on maps they tend to look like, they're often, they can be straight lines if they're very vertical. Obviously the flatter they get, the more they follow the topography, just like any other geological contact. And you might be able to measure the offset on the fault by looking at the geological map. If there's a distinctive boundary between two units which is offset across the fault, then we can use the geological map to understand how much motion there has been. So just to sum that up again here, these different types of contacts that we were just looking at, the four different major styles. There's the conformable contact, the unconformable contact, intrusive contacts, and faulted contacts. So let's think a little bit more about unconformities here, what they might look like on a geological map. And you can imagine that if we have a bedded sequence here, that if you were to tilt these and then erode it so that you would end up with this stripy pattern running across relatively flat topography here. And you can imagine also the structure contours within these different beds would look something like this, that they're dipping down towards the left in this particular diagram, and that these are, they're dipping down to the left. You can make a structure contour for the unconformity itself, and that therefore these structure contours are going to intersect the unconformity in the same way that, for example, they might have intersected the topography at the time prior to sedimentation. So then in our geological history, if we plop some younger rocks down on top of that, you generate this angular unconformity that you can see in the cross section here. We wouldn't, if it stayed like this, of course you wouldn't see the unconformity on the map. You'd just see the younger unit here, the younger sediment. However, in many instances, particularly onshore, we see that the younger units may then get eroded away. And when that happens, we end up with this sort of map pattern where essentially the younger stuff is rather flatter bedded. The older tilted material is exposed here, but there's this angular contact here between the old and the young that we see in this sort of T shape. And the more angular it is, the more like a letter T it looks like. If it's, of course, a disconformity, you don't get that geometrical arrangement. Yeah, and then this is, I guess sometimes it's called overstepping, but we don't need to worry about that too much. So let's look at some actual geological maps. So you will eventually come to look at these yourself. And so these are some examples. You can see this sort of pinky spotty unit here is the younger sediment, and you can see this irregular contact here where it's sitting on top. This spotty unit is sitting on top of a whole bunch of well bedded and dipping rocks. You can see these are 60-degree dip. It doesn't show the dip on this one. It's actually partly following the contours, so it's relatively flat bedded. So essentially we've got a dipping set of sediments here and this flat bedded stuff on the top with an angular unconformity. And likewise over here, this again spotty looking stuff here in the pale buff colour, it's sitting on top of this reddish material with the dark green dikes here, and you can see how they're again making this T shape on the map where they run straight, well, they're going under the bottom of this deposit, but at the map surface we see an angular arrangement there. Okay, so usually, but not always, the unconformity surface is going parallel to the strata above it. This is an example here in a mine. You can see the base of that, so that's more wiggly, and that's so unconformities don't always have to be completely flat. They can be irregular, and that's because they represent an erosion surface, and of course sometimes your erosion surface is not perfectly flat. You may have hills that were formed in the geological past that have then been blanketed by younger sediments, like in this one, this version here. And then, so if you do have sloping topography under the unconformity, and the sediments then are gradually filling up that topography, so the bottom of the hill is buried essentially by this dark blue unit, and the light blue one, the youngest one here, is essentially stepping up on top of the old eroded hill. Sometimes we call this an overlap. So again, here's an example where we've had a tilted sequence here with an unconformity, and flat-bedded rocks are sitting on top of this. So this is an angular unconformity, and these are two examples where you can see overlap here, and then where we see essentially the younger sediments sitting on top of two of the older ones. That's what we call the overstep. So, things that we can do when we are describing unconformity. This is a cartoon example with the ABC are the steep bedded stuff, the older material. Then the unconformity is formed, and then we have again a younging upwards. So Y is the oldest one and Z is the younger one here. And we can measure the orientation of the unconformity. Just like a bed, you can measure its strike and its dip. You might want to figure out, is it an angular unconformity? Is it a disconformity? This one is clearly an angular unconformity. And then when we look at the map, you're also trying to assess which units are above and which ones are below. And essentially, if you know the ages of that, you get to potentially understand how much time is represented, how much is missing. So finally we come to look at igneous intrusions, and as I mentioned before, there are these three different styles that we see: the sill, and the dike, and the pluton. So the sills are flat bedded and parallel to the stratigraphy, and the body itself is tabular. This one shows them perfectly horizontal. They're usually not perfectly horizontal, but usually sub-horizontal would be typical for a sill. A dike is generally high angle and critically has to cut across the bedding of the stratigraphy of whatever unit is intruding. And the pluton tends to be blobby. It's not tabular like the other two. It can be like a big round mass or irregular form, and again it does have to cut across the stratigraphy. If it doesn't cut the stratigraphy, then an igneous body is termed a sill. And we can use these characteristics, of course, to identify things on the map. So sills, of course, will be going parallel to the stratigraphy like that. Dikes are very typical. They cut, usually if they're high angle, which they often are, they are cutting both the stratigraphy here, but also the topography as well. They just look like somebody's taken a marker pen and drawn up, in this case, a big black line across the map. And our plutons, the big blobby plutons, are doing what one would expect. They cut across both the stratigraphy and the topography, and they have this like irregular mass. They're not tabular in form, they're not geometrical. So once you get all these different aspects of the map identified, you can start piecing together a geological history. And we do this by looking at the relative age relationship. So when we do that, we don't need to know the actual age of the sediments or the igneous rocks. We just need to know their relative age. And we can do that essentially using a geometrical approach. You don't have to, you can add the absolute ages later, maybe through using the fossil assemblages or radiometric dating, something like that. And the real key to all this is looking at like a cross-cutting relationship, right? So if something cuts, if one feature cuts another one, this means that must be younger. Just like cutting up a cake, you can't slice a cake until you've made the cake. And the same thing is true of strata. It has to be deposited before you can deform it or intrude it or fault it. So like this is an example, a map here with two sets of sedimentary sequences and two igneous bodies. They look like dikes here, and essentially what we can piece together here is the deposition of first the older sequence, which would be this colourful pinky purple colours here. We don't know immediately looking at this which one is the bottom and which is the top. That can be worked out, but this sequence has been deposited and then it has been tilted. Right, we know it must be tilted. It's dipping. You can see it's cross-cutting the topography. We know it's been tilted, and then it must have been intruded by this dike, the one on the left here. So this dike is cutting these older sediments. So we know it's younger than the sediments, but it doesn't cut these blue sediments. They must be younger than the dike. So then we must have had an erosion, because here you can see the T shape here. This shows the angular unconformity. So we know that the unconformity, the erosion, is younger than the dike. And then we get the deposition of the blue sediments, which are much more flat-bedded. You can see they're basically following the topography. In this particular case, they're pretty much horizontal. And then in turn, they have been intruded by this dike here, and then the whole thing must have been eroded again. Because we now see them at the surface. They're exposed. This would not have been erupting onto the land surface. That has been removed. So there's been some final erosion. So two stages of erosion there. So once you've got your brain around that and decided which is the oldest and which is the youngest, you can visualize this using a generalized vertical stratigraphy, which I'm going to be asking you to do with some of the maps you're going to be dealing with over the next few weeks. So they are sometimes more complicated than what you're going to be doing on real geological maps, but they are a way of summarizing, showing the stratigraphy in a simplified form. They are represented as columns here, and each different unit is represented by a different color. And there's also a vertical scale here, so it shows the thickness, the true thickness of the sediment, not the apparent thickness. And they are useful if you make them in different places. It allows you to correlate from one place to the next and compare different areas. So in a very simplified form, you would stack up, you'd figure out which order your different units have been deposited in. In this case, A is the oldest one and E is the youngest one. And then we have to try and scale the diagram to put a vertical scale on the side so you can see how thick each one of them is. And we tend to then also leave a gap for unconformities, for missing time. This is another good example where you need to use colours and use the same ones that you used on the map. So as you may remember from previous exercises, we have to calculate the true thickness, so that's perpendicular to the bedding. So you can maybe calculate the vertical thickness. If we know the dip of the bed, you can then calculate from the dip and the cross strike distance the true thickness of a bed, and that allows you to scale your generalized vertical stratigraphy. So something, for example, like this, where the A is the thickest one. In this case, this doesn't have a scale because it's just schematic, but here you can see the A at the bottom is the oldest one, E at the top, and we have an unconformity here that is depicted by this wiggly line and a little gap. But it is critical when you do these to leave these gaps and also to make sure there's a vertical scale. The colours should probably reflect those on the map. And we need some sort of a width to it, right? It can't be pencil thin, it has to be. So the way to go about doing this is to essentially figure out the order in which the sediments were deposited, then you calculate how thick they are, and then work out a scale that fits onto your piece of paper, right? If the piece of paper is 25 centimeters long, you obviously need a scale that will fit onto that, and you need to find a way to scale your true thickness to the scale you're going to draw it in, and leave a little room there for the unconformities where you can put the wiggly line. So for example here, we would have here between C and D, there's the unconformity. That's when the erosion and uplift occurs. And then you need to draw the a width. That's pretty arbitrary, but use a little bit of common sense so it looks a bit like this, and then you color it in. Great, so that's all I have for this week, and in this week's exercise you're going to practice these things I've just been talking about, to draw structure contours, draw a cross-section, make yourself a generalized vertical stratigraphy, and then write an interpretation. Okay, good luck with that.